Hello students. Um, I'm going to cover some topics really quick, several chapters. I'm covering so much ground this week that I'm going to just give you a synopsis of each chapter right here. Okay? Okay, here we go. As you know, I have a full-time job as an environmental engineer, and from 1999 to 2003, I spent much of the time studying fractures, cracks, and anything karst on Camp Bullis, because we wanted to make sure the stuff the Army buried in the ground many years ago, World War II even, um, was not moving and especially not harming anyone. Well, I was glad to know we didn't find problems while I was there. But I learned tons from a karst expert, Dr. George Veni, Veni. He's on Google, he's on YouTube, so you can check him out. My face isn't there, but his is. He taught me almost everything I know about karst. Running water and groundwater is discussed in Chapter 5. It's exactly why I studied karst. Dr. Vini taught me that it is not studied very well. The world lacks much information about how water flows underground. San Antonio benefits from a vast underground source of fresh drinking water. It is known as the Edwards Aquifer. Sedimentary rock built San Antonio. One of the younger stratified layers is the Edwards limestone. There are three older layers that I remember. They are the layers perched above the Edwards limestone. The Glen Rose limestone is one of those older layers. There's the upper Glen Rose, the lower Glen Rose, and I cannot remember the third limestone layer that forms something called the Trinity. They are layers perched above the Edwards limestone. The Glen Rose limestone is one of the older layers. We benefit from a higher perched source of drinking water there. It's known as the Trinity Aquifer. Trinity refers to three layers of older limestone. Am I boring you? I hope not. Anyway, it was good that I got that experience. I feel like I can take it and convey it to you through these lectures and maybe face to face if I ever meet you. Anyway, the running water that recharges these aquifers are the main ingredient that shapes the caves underneath and shapes our surface landscape. Mixing water with carbon dioxide trapped in our limestone, and limestone's main mineral, calcite, helps speed up the process of eating away the hard rock. That's why we have so many caves around here. You may have been in one, may have taken a tour of one. Most of the caves are dangerous, and we are not allowed to go into them. But let me back up and generalize this chapter, Chapter 5, Running Water and Groundwater. Running water and groundwater opens with an examination of the hydrologic cycle and the exchange of water between the oceans, atmosphere, and land. The discussion of running water includes an examination of drainage basins, river systems, and the factors that control stream flow. Erosion and transportation of sediment are presented, including erosional and depositional features of narrow and wide valleys. Running water concludes with a look at flooding and flood control measures. After an examination of the importance, occurrence, and movement of groundwater, springs, geysers, wells, and artesian wells are investigated, following a review of some of the environmental problems associated with groundwater. The chapter then ends with a look at the formation and features of caves and karst topography, which is how I started this discussion here. Then we move on to Chapter 6 and divert ourselves to glaciers deserts, and wind. Wind is my second favorite scientific topic. But let's talk about all of those in chapter 6. Glaciers, deserts, and wind. This chapter begins by examining the types, the movement, and the formation of glaciers. Also presented are the processes of glacial erosion and deposition, as well as the features associated with valley glaciers and ice sheets. The Pleistocene epoch and some indirect effects of Ice Age glaciers are also discussed. The section closes by examining some of the theories that attempt to explain the causes of glacial ages. It's a fascinating topic. The study of deserts begins with a review of the roles of weathering and water in arid climates. A discussion of the evolution of much of the basin and range region of the United States provides insight into the processes that shape desert landscapes. The chapter ends with an investigation of wind erosion and deposition, including the various types of sand dunes. So after we go over 4 topics, running water, groundwater, and then deserts, glaciers, wind, we'll go into my favorite of all scientific topics, and that's chapter 7. Plate tectonics. It's a scientific revolution that unfolds. This chapter opens with a discussion of historical views about the placement of continents and ocean basins. It continues by examining the lines of evidence that Alfred Wegener used in the early 1900s to support his original continental drift hypothesis. And remember, the word hypothesis is very important, as opposed to a theory or a law. Law, theory, hypothesis. This evidence included the fit of the continents, fossils, rock types, structural similarities between continents and paleoclimates. Also presented are the main objections to Wegener's ideas, particularly the lack of a driving mechanism. Following a brief overview of the theory of plate tectonics, his was a hypothesis. Alfred Wegener's was a hypothesis of continental drift, but then we moved into a theory of plate tectonics. It's examined in detail. The distinction between Wegener's idea of continental drift and the science of plate tectonics is addressed, and the movement of lithospheric plates and different types of plate boundaries are examined extensively. This chapter looks at the features associated with different types of plate boundaries and how these features shape Earth's surface. Ages and distribution of ocean basins, sediments, hotspots, and paleomagnetism are used to provide additional support for plate tectonics. The chapter closes with comments about the driving mechanism of plate tectonics. If you can understand plate tectonics, you will understand why we have volcanoes, volcanic eruptions, earthquakes, why climate changes. It really helps you understand why climate changes. It's a big topic. That's why it's my favorite. But moving into chapter 8, I take you to earthquakes and Earth's interior. This chapter begins with a brief description of the effects of the major earthquakes that have taken place in California within the last 10 years, following an explanation of how earthquakes occur, the types of seismic waves, their propagation, and how they appear on a typical seismic trace they're presented. This is followed by a discussion of earthquake epicenters, how they are located, and their worldwide distribution. Earthquake intensity and magnitude are also explained. Magnitude meaning, say 4.0 on the Richter scale. That's magnitude. Or 10.0. What's the difference? When is bad, bad? The destruction caused by seismic vibrations and their associated perils introduces a discussion of earthquake prediction. The chapter closes with an explanation of how earthquakes are used to discover Earth's interior structure and a brief description of Earth's interior composition. One of my top 5 favorite movies is The Core. It's a Hollywood movie, but it's one of my top 5. Okay. With the understanding of plate tectonics, like I said, it helps you understand earthquakes. It will also help you understand Chapter 9. So you can see how Chapter 7 is pivotal in my view. If you go to Chapter 9, it just continues the theory of plate tectonics. It explains why volcanoes and other igneous activity occur. And so in Chapter 9, it begins with a description of the catastrophic 1980 eruption of Mount St. Helens, May 18th, 1980. I remember it. A discussion of volcanism and the factors that determine the nature of volcanic eruptions, magma composition, temperature, and amount of dissolved gases is followed by an examination of the materials that can be extruded during an eruption. As you study about Mount St. Helens, please understand that it really did happen. So the things that I talk about to you in class, in these virtual classes, and also what's in your book, these are real occurrences. That's what's beautiful about science. You know that we only go by what we actually prove and actually see. The types of volcanic cones, their origins, shapes, compositions, as well as the nature of volcanic landforms are also presented. And the one at Mount St. Helens is a very, I remember it. You can't forget it. So in this chapter, an examination of intrusive igneous rocks. The activity of intrusive igneous activity includes the classification and description of the major intrusive igneous bodies. Intrusive meaning it's igneous rock that formed below the surface of the earth. It took longer to solidify. Okay, so it's very rough, very coarse. And those igneous bodies, the major intrusive igneous bodies are dikes, sills, laccoliths, and batholiths. Okay, the chapter closes with a discussion of the origin and distribution of magma and the relationship between plate tectonics and igneous activity. You see, plate tectonics. So moving with the theory of plate tectonics, we can start talking about the actual crust of the earth, all right, and how it's deformed, crustal deformation, and also how mountains grow, how they're built. Crustal deformation and mountain building is chapter 10's about. So this chapter begins with a brief examination of the processes of crustal deformation, including the factors that affect rock deformation. I was always raised to understand that all rocks, no matter which one you pick up, they have a crack in them. They're deformed. The various types of folds, anticlines, synclines, domes, and basins, those are important words. I want to make sure you understand those. Not going to do it here in this video, but I want you to understand it. And then the idea of faults. Faults are like both dip slip and strike slip faults. They're investigated. Mountain building at convergent boundaries is discussed in detail, including subduction, continental collisions, and accretion of terrains or terrains. Terranes, terrains or terrains. So the chapter concludes with a discussion of fault block mountains and the concept of isostasy. Okay, that's a lot of 50-cent words there. I'm just throwing them out there because I'm generalizing the entire chapter. All right, that word terrains you've already been familiar with because we talked about glaciers above in the previous chapter. Okay, I think it was chapter 6. All right, terrains. All right, so with this, all this formation that we've been talking about and deformation and mountain building doesn't happen in days. It doesn't happen in weeks. It doesn't happen in hours. It doesn't happen in months. It doesn't even happen in years. It happens, no, not hundreds of years, not thousands of years. It happens in millions of years, geologic time. So that's why chapter 11 is devoted to geologic time, to give you an idea of how fast things occur, or in my view, how slow things occur, how important they are to you and me. Okay, geologic time. This chapter opens with a brief history of geology that spans the period from James Ussher, mid 1600s, to James Hutton in late 1700s, and Sir Charles Lyell in the mid 1800s. The chapter continues with a discussion of the fundamental principles of relative dating, including the law of superposition, very important law, principle of original horizontality, the principle of cross-cutting relationships, and the uses of inclusion and unconformities. Okay, big words, I know. So how the rock units in different localities can be correlated is also investigated. I'm going to stop here in my little talk about this chapter and just say, look, we try to figure out what happened. How did the rock get formed the way it looks today? How did it happen? That's what all this is about. In geologic time, what did it take in order for the rock to look the way it is so that we can benefit from it? Why are we benefiting from certain types of rocks? How did it occur? What is going to happen in the future? That's the real ticket, right? The types of fossils and their significance to understanding geologic time precede a discussion of the conditions favoring preservation. Also examined is the use of fossils in correlating and dating rock units. I already mentioned relative dating, but we also have something called absolute dating. I'm going to give you a definition right now what the difference between dating a rock. That's a relative date and an absolute date, okay? A rock formation that is 20 million years younger than another rock formation is relative dating, relative age dating of that rock. I mean, it's associated, as you associate it with a different rock layer, maybe the one above or below that rock layer in sedimentary rock, if it's 20 million years younger, then that is relative to the other one, okay? But I can look at that one rock layer and say that it is 50 million years old. If I tell you the absolute age of that rock layer, that's absolute age dating. Relative age dating is, to me, better because it can tell the story of how the rocks formed. All right? Following all of that discussion in chapter 11 is an explanation of radioactivity and the fundamentals and importance of radiometric dating. They're presented because the only way we can actually tell you the age of rocks is to look at the radioactivity of the rocks. Yes, rocks are radioactivity, or I should say they contain radioactive elements that we can capitalize on, because radioactive elements, they don't go away overnight. They stick around for a very, very long time, and they slowly fade away. They take millions of years to reduce in quantity. As a matter of fact, for example, uranium takes several million years for half of the quantity that we started with to go away. And that's good because we can get a pretty good rate, a pretty good idea of how fast the radioactive elements go away. And if we can measure what we estimate to be the original quantity, measure what there is today, if half of it's there, then it's gone through one half-life is what we talk about. And we could say that that rock is X million years old based on radiometric decay. Okay, that's how we do it. The chapter concludes with an examination of the geologic time scale. Alright, I'm going to pause here. I'm going to get the book out and talk about chapter 12.